All right, so we're going to look at a couple of different models of the atom, the Bohr model versus the wave model. Now, you know what the Bohr model is. You've seen versions of it before. So Niels Bohr constructed this model to explain some of the sort of mysterious things about quantum mechanics and to reconcile that with the atom. We have the nucleus, which is positive, and we envision the electrons, which are negative, as being in these fixed orbits around them. And the energies of these different levels, n is 1, n is 2, etc., can be written down simply like this, where Z is the atomic number, which would be the charge, n is the level, and RH is called the Rydberg constant. And this is what is in the Rydberg constant: the mass of the electron, the fundamental charge, the permittivity of a vacuum, Planck's constant, and the speed of light. This was calculated. This was all figured out by Niels Bohr in trying to balance the energies. It's equal to 13.6 electron volts. Now, here's something interesting. You could ask the question, why doesn't the electron do that and emit energy? Why doesn't it just go stick to the nucleus and radiate? And, that would mean the universe doesn't work the way we think it does. The reason is because Planck's constant is a constant, and you cannot have smaller energy than that. That sort of enables that model to hold together. But it's not that good a model. It has problems. It works for hydrogen, for example, which has one electron. You can put that electron at different levels. It works for ions that have one electron. That is, you pull everything off, except the last electron. And it isn't good for much else. It just isn't accurate because it can't account for some of the subtleties. It's a primitive model. It's obsolete. It's an antique. Unfortunately, its image persists in popular culture, and unfortunately in textbooks also. There are no dots, there are no circles in atoms. Those are primitive conceptions. And they've been primitive since the 1930s, when they were replaced. So you probably have seen this. You probably had to do this in high school, where you draw a circle and you put dots on it for how many electrons are there, right? And you put a number of dots that are appropriate to that level, like this level can have this many dots, etc. Anyway, that's not a good model. There are no shells. Shells is a word, electron shell is a word that persists. They don't exist. There are no subshells. These are misleading words. I find them misleading. I think they're wrong. I think you should not perpetuate them. So forget this picture. We're going to replace words like shells and subshells with energy level, which is the only appropriate way to describe them. Okay, let's take a look at waves. So a standing wave is a wave that exists between boundaries. And if it were a mechanical wave of some kind, we could look at these sort of walls as being a fixed boundary, and the wave is going to exist in between it somehow. And it could even be like a spring bouncing between it, or like a guitar string or something. So the simplest, lowest energy sort of vibration we could have is one where it just sort of goes back and forth. Another higher vibration would be like this, maybe with sort of 2 areas of amplitude, then maybe one with 3 areas of amplitude, like that. And you can recreate these with sound waves, and light waves behave like this, and the strings on musical instruments. So there are a fixed number of nodes when you do this. When you define the boundaries like this and say the wave can only exist between the boundaries, you have a fixed number of 0 amplitude regions. That bottom one has no nodes. There's a fixed wavelength, because you can only fit whole numbers inside those boundaries. And as a result, there's a fixed energy too. So you're only allowed to have whole number multiples of energy. And it turns out that that was known about standing waves. And the people working on atomic physics said, hey, look, let's apply this wave equation to an atom or to an electron and see what we get. So we get what we call the wave equation. This was done by Erwin Schrödinger. It's very simple to write in its sort of abbreviated form. H psi equals E psi. That H with a line on top, that little caret on top, is called a Hamiltonian operator. Psi is the wave function, E is the value for the energy that you get, and you get the product of the energy and the wave function you started with. Now just if you're curious, that operator looks like this, at least in one form. It's Planck's constant over 2m. That's a partial differential operator. That's what it would look like in one dimension, and it's time independent, so you only see the x variable in there. So it's a second order partial differential operator, which unfortunately is usually the first differential equation you see dropped in your face when you're an undergraduate studying chemistry, when you need to build up to that. What that Hamiltonian operator does, developed by William Rowan Hamilton, gives you the total energy of a system. Well, especially if you include the potential term right there, V, which in this case would be a Coulombic potential for electrical interaction. Total energy of a system. All right, so a function, you're familiar with functions from algebra classes, such as y equals mx plus b, the equation of a straight line. It's a function. Put a number in, you get a number out, right? A differential equation, like the wave equation, or the Schrodinger equation, what you do is you put a function in and you get a number out, which is really different. And this is how differential equations work. It's not just a number. You're looking for a function that solves the equation. So we say that a function is a solution to a differential equation. So you write down the equation, and then you try to find out what function fits into that to make it a true statement. And that is not trivial, believe me. It's not easy to do for that particular equation. But what you get out of it is the wave function. And you can write neat little wave functions like this for the hydrogen atom. Here's an example of one. I'll explain this in a minute. So psi, the wave function, and that E is the exponential E, not the Coulombic charge. Okay, so A naught there is called the Bohr radius. It's the lowest energy level. And the little r is the actual radius it's the radial dimension of this function. So we have a radial part, and we have these two angular parts, two different angles that define this thing in 3 dimensions. So if you had a radius like this, the angle theta would go around that way in that plane, and the angle phi or phi would go around that way. So those 3 dimensions, r, theta, and phi, define the 3-dimensional space in which it exists. So these radial and angular components, and incidentally, that was just one example of one wave function. There's a bunch. They give you, and they also define the allowed values for the energy of an electron. And they also give you sort of its spatial distribution. They define where in space the electron can be found, where it's located in space, if you will. All right, now, what you get from that, just like with a standing wave, you get fixed whole number values for the energy. They are only allowed to be fixed whole number values, and from those, you get what are called quantum numbers. And we'll explain that later.